Good morning, students. And today we'll be looking at using convolutional neural network to process text, right, and perform classification, right? So in the previous tutorial, we have go over how the LSTM can be used, right? And by sharing a network called W, then you can actually carry information from the past to the future, right? Using just one W, right? So LSTM has an idea of a shared network, but now the idea of CNN is that we can run a moving window and try to capture the relationship between bigrams or trigrams, or etc., and then try to concatenate these features and try to predict them, right? So right here, I'm saying that you can imagine that the image is something like 48 by 48, and we can actually move a kernel of filter, right, of 3 by 3, and moving it left to right, and then combine all this resulting features to get some information, right? In the same way, we can actually run filters of, for example, 1 by 2, right? That can actually look at 2 sequential words in a piece of text, right? And then by that way, we can, by combining 2 words, then we can get a number, right? But of course, if you don't understand for now, don't worry, I have some pictures down there. It should allow you to better understand this, right? And in this part, what we're going to use is basically using multiple filters of different sizes, which will look at 1 by 2 bigrams using a 1 by 2 filter, trigrams, 1 by 3 filters, and n-grams, right? Etc., right, when in the text, right? By combining all these features, we can capture a lot of interesting characteristics of our text, which can then be used for classification, right? Okay, and today, luckily, we don't have to do too much of coding because a lot of the information will be the same. The major part that we have to code is the CNN network, and otherwise, a lot of the things will remain the same. All right. So firstly, we will be. So let us first look at what we're going to do today, right? So that will be doing the ET out, right? Extract, transform, loading, EDA, which will everything will be the same, right? So that's why you can see a lot of cells already written here. We're going to do a lot of tokenization, numericalization. We'll be using the same code, FastX embeddings, preparing data loaders, right? But the majority part of this tutorial will be focusing on how we process CNN, right? And we can have some pictures right here, right? And then training and test will be mostly using the same code, but there's some adjustment, right? Because the input now is to the CNN, all right? So great, so why not we make this a little slightly big, and then we can run this line of code, right? So this is basically setting the device and the seed, right? And hopefully, let's wait. All right, and yeah, just to make sure you guys know the version I'm using. Torched on. All right, so those are the versions I am using for my tutorial this time. And if you have actually a device, you should certainly run this. And I already typed this, so I can remove it nicely. Great. So those are my setup. And then for those who don't remember, why do I have to have seed? Is simply because you have to, in your research, you have to run this maybe three or 5 times, right? and then average the results, right? That would be the right research practice that you want to do, because you may get lucky in your randomization in the data loaders, right? And we don't want that, right? Great. So now we are done with that. Now we can load some data sets, and we'll be sticking with news classification we did last time. All right. So this is the training and the testing set that we have ready here. Now we can go to the EDA, and we can take a look at the training set. We can take a look at the unique label we have, and recall that our data set is quite big, 120,000, right? And what we're going to do is we're going to just limit it to only a small size, which is 24,000. And similarly for the wall set is 12,000, and for the test set will be 7,600. All right, so I think that is something we have already done in the last tutorial. Now we can look at the tokenization, right? And again, we are loading the SpaCy to help us build a pipeline for processing text. All right, so now we have load tokenizer. We can also do the numericalization, right? And we're going to use this helper tools to quickly create our vocabs, right? And this is basically the same thing we have done previously. It's gonna take a long time, so I'm gonna pause my video. Okay, great, it just finished, right? And then checking, and then we can reverse the mapping. And of course, you can see that these are the words that are unknown, and it will get a number of 0, indicating that it's Ankh. And of course, we got the special symbols, and the total number of vocabs we're going to have is 52,000 roughly. All right, so now we are done with pre-processing. Now we move to the fast text embeddings, right? And again, we're going to use torchtext.vocab, right, which contains a fast text embedding, and we're going to use the simple version of fast text, right, which is small and good for our demonstration, right? But if you use for your industrial purpose or research purpose, then you probably want to use something else, right? And you're going to take some time to load this. And you can see that once you load, there will be something called vector catch here that actually holds the embedding. And then now you can actually apply the vocabs to the fast vector. So you only retrieve the fast vectors that your vocab has, right? Now you can check that you have all the embedding. Each of them is a size of 300 for each of this vocab, right? Some students ask why 300. Well, actually the authors probably experimented with 300, 500, I'm not sure, 1,000, right? And of course 1,000 would surely be better than 300, right? But when you compare it, when you try to take the trade-off between efficiency and accuracy, right, 300 is not so bad. All right. Now we can move to the data loader, and again, I think this is basically the same, right, in which it takes the sentence, tokenize into words, and then convert them into numbers, right? As for label, we simply -1, and that should be our label pipeline. And right here, it's just a demonstration of the text pipeline and also the label pipeline. Now, this is something we did last time, right? Which is the collate batch. And this will be the function in which we're going to use in the data loader, right? In which the data loader will split our data set into batch. But this is the actual thing that's going to happen when we process our text, right? And one thing I want to highlight is that everything is the same. We still return the label, and we also return the text list that is being padded. But otherwise, there's one thing we actually remove, and that is the link, all right? Because recall that the links are used for the pack, the pack padded sequence. And since we're not using LSTM, we're using CNN, we don't need to pass the lengths anymore, right? So that would be something you have to take note of, right? And again, this is the data loader, the batch size is 64. And once again, I'm not sure I can clean this up to make it easier, just one line. Right. And for shuffle, like we have discussed, right, shuffle is not really necessary for a valid and test loader, simply because they won't actually make your model more robust, right? But certainly for train loader, because your model will be more robust by not taking the order effects into account. All right. So now we have, and then we can certainly take a look at our label and the text. It's very important that you always remember what is the input shape of the text, right? Which will makes you become expert in this area. That is, you be aware of the shape of different inputs, right? Great. So the label is a batch size, and the text is a batch size, comma, sequence length. All right. Great. So I guess the only part we have fixed, we have changes in the collate batch, which we deleted the link. Right. So now I think we come to the I guess the highlight or the main story. That is the model, right? And this gonna explain how we're gonna actually run a CNN on top of text, right? So imagine that we have this sentence, right? I hate this frame, right? And each of them, let's say, has an embedding size of 5. All right, for no reason, simply because this picture is easy to draw when the embedding size is not so long, right? So let's say we have 4 words, and each of them has an embedding size of 5, right? So you can imagine this is numbers, 5 numbers that actually represent I, right? And these numbers could be trained, or you just initialize, right? And you want to train together with the CNN, right? And then what you can do is you can actually so let's say that you can consider, so you can actually consider this as a 4x5 image, right? Actually, that is something you can imagine, right? Or you can no need to imagine, depends on you, right? Then what you can do in CNN is that you can initialize a filter or kernel in which the height is 2, all right, and the width of the height of the kernel is 5, right? So what is the meaning of 2 and 5 here? 2 is a hyperparameter you have to tune, in which it depends on whether how many words you want to look at one time, right? So in this case, I want to look at 2 words at the same time. So I'm actually looking at a bigram relationship, right? So if I change the kernel height to 3, I'm actually looking at 3 words at the same time, right? So this is the meaning of 2. And then what is the width here? 5. Well, we just want to take into account all the embedding, right? So now here we can take a kernel width equal to 5, right? There's one more input to the convolutional linear layer, and that is input channel. And you have to be aware that normally in image, the input channel will be 3, right? Because we're going to have R, G, and B, right? But in text, we only have one channel, and that is the basically this image, right? So in that case, input channel will be 1, right? So how the operations will look like, right? So this kernel, this yellow thing, there's a 10 box here, right? Will be filled with numbers, right? So you can imagine this is a 1, 1, 1, 1, 2, 2, 2, 2. I'm not sure any numbers could be the thing, right? And then the embedding here, it will also be represented by numbers, right? So it could be 0.2, 0.4, etc., 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 right? So what does this kernel do? Well, you take the kernel, right? So this number, the yellow number here, multiply with this number plus this number, multiply with this number, and this number, multiply with this number, and so on until the last number. That is, you take this number and multiply with this number and add all this addition, add all this multiplication, right? And then you'll get one number, right? So what is this one number represent? This one number actually represents some kind of relationship between I and hate, right? So that is what I'm trying to say, the bigram relationship, right? By multiplying them, we try to find whether there's any relationship I hate, right? That will be useful for classification, right? And you don't have to worry whether the kernel will have the right number, right setup to multiply and get something useful, because we're going to train this backpropagation, and the backpropagation will train the kernel to be the right numbers, to pick up the right signal from the embedding, right? So that is the idea. So now, once we have that kernel, right, as the follow, as a convolution, if we set the stride equal to 1, it would just move down by 1 pixel, and then it would try to capture the bigram relationship between hate and this. We got one more number, and now you're gonna move down again and get one more number, right? In total, we will get three numbers, right? And the calculation here is basically 4 minus 2 plus 1 equal to 3, right? So that would be the math in which we're going to know how many numbers we're going to have after we convolute, right? But anyway, what we're going to do in our tutorials down there is we can initialize filter of height 3, 4, 5. So we're going to have height of 3, 4, and 5, right? So that we can capture trigrams, 4 grams, and 5 grams, right? And then, so we're going to have 3 numbers here. Now, what we're going to do further is that we'll be actually doing max pooling here, right? So once we have 3 numbers here, we'll be max pooling them to get the most powerful features, right? So right here, for example, I have a relationship between I hate and I got 0.3. I hate this 0.6, and this stream is 0.9. And I found that the biggest activation that I found is this stream, right? Which will be very useful for classification, for my classification purpose, right? Then I just max pooling and I get the 0.9, right? So I can also perform max pooling later on my procedures, all right? So yes, so that something I'm gonna do. And so in a nutshell, very, very simple, right? So yes, so let us try to write this code together to gain more understanding. All right. So firstly, we're gonna do import torch.nn as nn, definitely, and import torch.nn dot functional as f. Okay. And then we're gonna start creating our CNN class, right? Which is right? And then we always need our forward function. All right, so now we have our CNN, right? And now we are ready to actually run this, right? So the first thing we're going to have is the embedding layer. They're going to make sure that we're going to convert all my text, input text, right, into embed them. And I will also make sure to mention what is my padding index, right? So input them and embed them. All right. Now we're going to create 3 filters, right? The first filter will be self.control 0 equal to nn.control 2D. In channels, again, like we said, is 1. And out channels is basically end filters, right? So we're going to have this end filters. We're going to pass it later on. And then kernel size equal to filters sizes 0. Embed them. All right. So this is basically how many filters we're going to have, right? So we maybe, for example, here I have, even though I have just 1 filter, right? I can have many of this, right? To capture different bigram relationships, right? That can focus on maybe this filters, even though it's a bigram, it can capture like pronouns, verb relationships. Maybe I can also have another bigram filter, right? That can try to capture maybe co-reference relationship, right? So you never know, right? And you don't even need to know which filter capture what relationship, right? You just need to specify the number of filters for that same filter size, and the CNN will try to capture as much relationship, and that will be useful for classification, right? So we have to make sure we have this end filters, and we also have to make sure that we have this. And filter size is basically we're just gonna later on do something like this, right? Something like basically 3, 4, 5 like this. The kernel size is 3. So this is the height, right? And then this is the width, right? Just like we say here, right? So here is the height is 2, and the width is, in our case, we want to start with 3 and then 5, all right? And we want maybe 100 of this, right? So that is the initial idea, but I'm not gonna define the filter size here. I'm gonna let the user define so that they have a lot of flexibility. Great. So now we have this. We're gonna do the same for convolution 1 and also 2. All right, and we're gonna change this to 1, and we're gonna change this to 2. Right. Great. So now we have 3 convolution operations. Each of them has n filters of kernels they're going to run, and each of them has a different height, right? So this is probably trigrams, 4 grams, and also 5 grams. All right, and then so that would be very nice operations to capture all the information, right? And then finally we're going to say FC equal to nn.linear, and this will be useful for the filter sizes times n filters output dim, right? And output dim again is basically I would simply put it here. Output dim is simply 4, right? Because we want to classify 4 types of news, right? And in this case, I expect that I'm gonna have information according to the number of filters, and I have 3 filters, right? So that's why I have 3 three times, let's say this is 100, then I'm gonna have 300 information, right, in which I can use to then put it into MLP, right? Note that why do we know exactly is 300? Because we use max pooling, right? So even though we have a long sentence, we will be very sure that it will always result in one number, right, for each filter. So that would also help us fix the problem if the length is very, very long. When we max pool, we will always get one number, right? So that's why it's exactly 300 here. Yeah. So that is a good things to mention. And then now we're gonna have some dropout, and we're gonna say dropout equal to some dropout. And I'm gonna add this to right here. All right, so that is the CNN. All right, and then now we can move to the forward function. All right, so we have three options, right? Embed, convolute, and max pool, right? And definitely maybe like cloud and then FC, right? That would probably something we have in mind. So for embedded, so firstly we have to make sure that we know that we have some input text, and the text is the shape is a batch size and sequence length, right? This is very good practice, students, to make sure that you always rotate down the shape to make sure you understand things clearly. I found that by doing this, it can make your coding much more organized, and also like you don't get crazy. Also, basically just write the shape down, right? Now you can embed it equal to self.embedding the text. So now that the embedded is basically batch size, sequence length, and embed size. All right, and then so we now get this. We have to and squeeze in the first dimension. You may wonder why, right? So, but let me, you know what this operation does, right? It's basically just create a one here, simply because if you send into convolution layer, it expect a 40 things like this, in which the first is a batch size. This is the input channel. This is the height, right? And this is the width, right? So this is the common setup for convolution, right? In our case, I think input channel is 1, and the height is basically, the height is always the sentence, right? And then the width is the embedding, right? So this is a perfect setup for us, right? Now we are ready to actually do the convolution, right? And this is very easy, right? So we're gonna do convol 0, right, equal to f.relu, right? And then self.convol 0 embedded, right? And then we're gonna squeeze not squeeze 3, right? We need to squeeze 3 is because of later on when we apply max pool, max pool only expect 3 dimensions, okay? But of course, if you're a little bit confused, so what is this? I'm gonna quickly write a shape, and then you guys will quickly understand what is the shape. But before that, let me just finish typing this. So I'm gonna just this and this. I'm gonna say convo 1, 2, and the layer is 1 and 2. All right. All right. So now we can work on the shape, right? So I can actually say that before squeeze, right? It will be each of this. I would say n is basically the shape is batch size, right? Definitely, and n filters and sequence length. Minus filter size n plus 1, right? So this one is nothing but basically we get it from here, right? 4 minus 2 plus 1. So that would be the result, the number. So we're gonna have, right? And we're gonna have and then of course comma 1, right? This one get it from so we it's just one number, right? Right. Because here we're gonna have one number here, right? One number here. Yep. Now, based on that one number, right? We just squeeze 3. So once we squeeze 3, right? I think you guys already can see what is happening, right? So once we squeeze the 3/3 dimension, then it's very clear that we don't have this anymore, right? Great. So now we are ready. So now we can max foo. So we can say foo equal to foo 0 f dot max foo 1 convo 0. And here is the kernel size, right? And we can make sure that with 0 shape 0. All right. So we're gonna basically max poo in this dimension so that it will add all of this add up, right? So basically, in this case, we have 3 here. So we just max the 3 numbers here into one number, right? So that's why the kernel is that shape, but by the way, I should put 2, right? And then finally, we're gonna squeeze 2, all right? And so, and then we're gonna do this the same for 3 of them. So this is 1, 2, and this one is also 1, 2, and the same for 1 and 2. All right, great. And of course, we can also take a look a little bit before squeeze. By the way, how do I know the shape, right? Well, one thing is if you get very familiar, you will be able to figure the shape. If not, later on I can show you how each layer works, and then you can also figure out very quickly the shape, right? Which is something that I really highly recommend the beginners to do this. All right. So before squeeze, f dot max the before squeeze, the shape is basically max foo batch size and futures 1, right? So it's basically you max this part, so you will only have a 1, right? Because you max them, right? And by squeezing the second dimension, you now have it's very clear that now is this will be like that. All right, good. So now once we have that, now we have to concatenate them first. All right. Otherwise, we won't be able to because now we have 3 features, right? And we can now concatenate them. So we're gonna say torch.cat poo 0, poo 1, and poo 2, right? and we're gonna basically it is very obvious that which dimension we want to concatenate, right? And that is n futures, right? So that is dim equal to 1. So we stack this many. So we're gonna have n futures times 3, right? So that's also matched to the n linear layers, right? In which we say 3 times. Okay, by the way, I quickly fix this one. Okay. Now we got this, and of course we can also apply self.dropout right here. So we're gonna say self.dropout. All right, and so we are done with the self.dropout right here. I'm gonna say dropout. And now we can return the FC. Right, so that is finished. Okay, so yep, so it's very simple as long as if you understand the basic theory, right? Then it should not be too difficult, right? So I'm gonna run this. So yes, so I'm aware that maybe some of you has difficulty, like you may understand like 40 to 50% what I'm doing, like how do you know the shapes? And then we can actually see how each layer works right here, all right? And that would actually create more understanding. So we can say, let's say we set the batch size to that, and then our sequence length is 456 for no reason. And then we can say input dim equal to length of vocab. And then we're gonna say input test, simply some input, right? Is a torch.ran in, right? One input dim. So we're gonna have batch size, sequence length. All right. So what does this do is basically create batch size of sequence length, right? So we're gonna do this, and then we're gonna have numbers from 1 to the length of the vocab, right? Which is the range of. So we're gonna actually check the shape, and this is the 64,456, right? And of course, I'm not sure you can do describe it like panda, right? I'm not sure. I don't think so, right? If not, then we can try to do the mean. No, we have to we can't do this, right? Dot max. Okay. So that is the biggest number, and then the smallest number is 2. Okay, so it seems like the numbers range from that to that. Okay, but anyway, we are now good. We have our input that we can actually test with. Now we can go to one by one, right? So we can try embed equal to nn.embedding, input dim 300. So this is basically simulating when we first get in the text and we send into this, right? And then we get this, right? So this is a very simple simulation, and embedded equal to embed input text, right? And of course, I did not run this. And then so we're gonna have embedded.shape right here. Right, and you can see that this is basically what we have discussed here, right? Right here. And definitely what we want to do is we want to unsqueeze, right? Equal to embedded dot unsqueeze. Actually, you can do in place here. You don't have to do equal at the first dimension. All right, so now once you do that, you will have 1 right here. Great. So now we are currently in this step, right? Now we want to do this thing. So what I'm going to do is simply copy this, right? So that I don't have to actually type a lot of things. So I'm going to say n futures is, let's say, 100. Okay, I gonna just define this, right? And futures is let's say I'm gonna have 100 of this, right, to capture 100 relationship, and future sizes is 3, 4, 5, and then the embed them is I'm very sure I already have embed them here. No, I only have input them 300. Great. So now I have this convolution, right? And now, okay, sorry. Now I can convol 0. So actually, I just go up here and copy what I have written right here. Right. And I don't need this cell because I'm just showing you guys what's happening. And then we enter this, and now we can actually take a look at the shape right here. And you will see that we got 64, 100, 454. And that is exactly what we have discussed right here. Yep. Yeah. If once you can see by your eyes, you start to believe, and you will never question it again. Yep. And definitely, lastly, you can try to max through this. Right, and then you can actually check the shape again, and you will see that it's 64, 100, right? So basically, all of this is summed together, right? And once you have all this, you can actually torch.cat, all right? 3 of them. Let's say I have only let's say I have 1 and 2 and 3. So I can simulate this like this, right? And I say that them equal to 1. And then I say something called A, right? Then A dot shape is basically 64. And then I have I stack 3 of them, right? So I got 300 right here. All right. So hopefully by going through this exercise, you guys can create a better understanding of the convolution, which is actually very, very simple, right? Below is more other versions that you can actually try to take a look. Right here, you don't have to actually write one by one. You can use some function called modulus, right? So please take a look. And then another version code that I actually created is called convol 1D. So that in that case, you treat the width as the input channel, and then the kernel size is only basically 2 because it's 1D. So the kernel dimension is only 1 dimension, and you need to put the kernel size to 2, and then the input channel is basically the width, right? So but anyway, they are the same and they work the same. I don't think any of them is more efficient or more effective. Basically, they are the same. So please take a look, right? But I just want to make sure that you know that convol 1D and 2D can achieve the same thing. All right. So those are something for your reference. All right, great. So now I think we are done. So I think we can quickly club this. All right. So now the rest is we don't really need to code a lot. We are done with coding. So right here, I'm just initializing the weights that I have similarly do it in the previous tutorial. One only difference is that I'm timing normal instead of orthogonal. While there's so many literatures, and it seems like timing normal is very useful for convolution, right? But you can read a lot of papers, or you can ask ChatGPT, and maybe there's so many versions you can use, right? So this is just example of the timing normal, right? But you can certainly look at the literatures. And then right here, I'm just simply initializing the model, applying the initial weights, and make sure I put the fast embedding to my embeddings. I count parameters. So my model here is 16 million, right? And then right here, I am defining my optimizer. I'm defining my accuracy function. And this function is basically pretty much the same, right? Pretty much the same. Of course, there's a little bit of shape manipulation right here. But I think that is very trivial. So you can actually run this, and also same as this one. And now you can okay, so give a it takes some time to actually count do the length, but I think you don't really need this, right? Because we no longer, okay, you need this, right? Because you have to, okay, sorry, you have to divide it by that. I thought this is for hours, Tim. Great. So now to make sure I don't have any errors, I need to make sure that I have this folder called models. All right, and so that it won't have any errors here. And then the rest is the same code that I have done earlier. I set the num epoch to 1, which is actually not supposed to be that. I think it should be at least 5 or 10. In natural language processing, the common epoch that we're gonna run is like 5 or 6, because our data sets is really big, right? So the common epochs we run is like 4, 3, 4, 5, right? But of course, in machine learning, like normal table data set, you're gonna run like 50 to like sometimes 1,000, right? But for NLP, you don't, right? But 1 is simply too little. But I'm gonna run this because I'm running on my MacBook. All right. So I'm gonna run this, and if there's no error, I'm gonna pause my video, and then I'm gonna come back when it's finished. Okay. All right. So I'm back, and after 60 seconds, I think it's done. And the first epoch does not look really good, right? It's around 35%. So, but I guess it's fine. You guys can try to run this at your home, but definitely now I'm gonna plot this, right? And I don't have any lines simply because I'm running only one epoch. You know what, guys? I'm gonna change my epoch to 2, and I'm gonna come back and run this again, and once it's finished, I'm gonna come back. All right. All right. So now I'm back, and I got sorry, I got 2 epochs done right here, right? So it's much better now. It's 54%. But anyway, if you keep running on this, I think you can get 90. Yeah. But one thing I forgot to mention is that you can see that per epoch is only 57 seconds, right, for CNN. But in the LSTM, it took me 22 minutes, right? I mean, of course, I'm using my MacBook M1, and it definitely is very slow. But you have to understand, you have to figure out now why CNN is much faster, right? One thing to point out is that LSTM, it has to always wait for the previous. It's a sequential model, right? So you have to move from H0 to H1 to H2 and H3, right? So by nature, LSTM or any recurrent neural network is very, very slow because they cannot be parallelized, right? But in CNN, it's not in that way, right? Because everything can be parallelized, right? You can see that if you look at, I don't want to scroll up anymore, but if you look at the picture that I have showed you, you can see that they are all independent, right? So they can be all run at the same time in different cores, and then concatenate the results later on through some memory mechanism, right? So that is the reason why CNN is much more faster, right? It doesn't mean LSTM is worse, but in terms of efficiency, it seems like CNN is much better. It also points out the reason why later on LSTM is not gaining that much of attention because it's not so efficient, right? But eventually, both of this will be replaced with transformer, which is very parallelizable. I mean, it can be done on so many cores at the same time, right? So transformer is very, very efficient, and then it can gain by doing that, it can gain more performance in less amount of time, right? Great. So that is some small information, but anyway, I think we can run this now. So now you can see that my train loss and validation loss, although this looks like a big gap, don't be fooled, right? It does not start at 0, so I guess that should be fine. And then accuracy, so it seems like the validation accuracy is even higher than the training accuracy, but I guess we only run for 2 epochs, so there's a little bit to be gained, and we can actually now evaluate our results. And let's wait. And so it's 53%. All right, so not so bad. And let me see whether I really have this model, right? So my model is basically CNN.pt right here. And of course, we can test on some random news. So firstly, you have to modify this to torch.tensor, right? And input it into text pipeline. Put them into a single list like this. And then, of course, put them into, you can actually take a look whether the mapping is correct. And definitely you have to reshape them so that the batch size is the first thing and the sequence length is the second, because this is the shape that we want to put it into the model, right? And then we just simply put into that, and then we predict, right? And it happens that it predict one here. I guess one here is I don't remember. It's something like world. I think this is world something technology and business. I don't remember, but anyway, it doesn't seem like I'm classifying correctly. So if you trained more epoch, you should be good to go. All right. So yes, I think it's very, very we are very successful in teaching CNN today. If you're confused, I recommend you to pause my video and go over, right? So today we look at CNN and how we can actually treat the futures as a way to look at text, right? So ETL, we load the data set, we perform some EDA, and we do tokenization and numericalization here. Fastest embeddings, data loaders, we actually delete the link, and we design the model in which we try to understand what the convolutional layer look at, right? So in 2D, the kernel height is 2 or 3 or 4, right? Basically, depending on which relationship we want, and the kernel width is the embed size, right? And we're going to have this filter many of this to capture different relationship in gram, different relationship in trigram, 4 gram, 5 gram, 6 gram, whatever you want, right? So depending on how you want to design this. Some students may want to question, like, how do you know you need to have 100? How do you know you need tri-filters, trigram, 4 gram? I don't know, right? We just try and it works, then it's good, right? So it's a matter of try and error. And so neural network is a half science and half intuition, right? Or half art. Yep. And then we perform some training and we do some tests, all right? So yep, thank you very much, and see you in the next class. Bye-bye.